As broadband internet grows more popular, video services like YouTube continue to expand. The number of online viewers was growing exponentially over the years from 2007 through 2013. The function that you see there estimates the number of online video viewers in millions from between those 2 years. T equals 0 represents the year 2007. We're going to give appropriate units on all of our answers below. Part A, estimate to the nearest whole number the number of online video viewers in the year 2010. 2010 is how many years after the start? So if the start is in 2007, 2010 would be 3 years later. That means we want to figure out what n of 3 would equal just by substituting in the value 3 into the function n. And you get 166.547. That's good enough. Now this is in what, millions? Millions of video viewers in the year 2010. Part B, find the simplified derivative function n prime and give the appropriate units. And so we're taking the derivative of function n prime is 135 times 0.07 times e to the 0.07t. Simplify by multiplying the constant 135 times 0.07 together, you get 9.45. All right, that's the formula or the derivative function. We're going to give the appropriate units. We are in terms of million viewers per, let's see, t is measured in years, so per year. Okay. Part C, at what rate was the number of online videos changing in 2010? Changing means how quickly is this graph going up or down? That's the derivative. In 2010, once again, that's 3 years after the start. We want to find n prime of 3. So use your derivative function from above, plug 3 in for the value of t. You end up getting 11.658 approximately. This is the extra viewers, extra millions. That doesn't really sound right. Let me fix this. Which means the next year, by the time we get to 2011, I would expect to see an additional 11.658 million viewers. Part D, in what year was the number of online video viewers increasing at the rate? So in what year, that's the value of t, was this quantity of viewers increasing at a particular rate? That's a derivative. We want to figure out where n prime of t is equal to the given rate of 12.5 million online video viewers per year. So we're taking the first derivative that we found up in part B, and we're going to set that equal to 12.5. Okay, so still getting used to this. So sorry. Okay, set this equal to, lost it again, 9.45 e to the 0.07 t. Okay. Solve for t. So what are we going to do first? I guess we're going to divide both sides by 9.45. And that gives you 1.32275. So that's equal to e to the 0.07t. I want to try to solve for t. It's in the exponent right now. We get it out of the exponent by taking the natural log of both sides. Okay, so now this is going to be equal to just 0.07t. The natural log undoes the e, and that leaves you with the exponent. And then I'm going to divide both sides by the 0.07. So when I simplify it, or rather when I approximate this answer, it's going to be somewhere around 4 years. T is approximately 4 years after the start, which was 2007, or this is the year 2011. Part E, what was the average rate of change in the number of online video viewers from the year 2010 to 2013? All right, 2010, remember that was 3 years after the start. 2013 is 6 years after the start. And so this is asking you for average rate of change, which is n of 6 minus n of 3 divided by 6 minus 3. And this is going to simplify all the way down to, I'll let you guys check me on this, 12.97 million viewers over this 3-year span. Okay? Here, let's put more. 3 million more viewers over this 3-year span. Okay. That takes care of that problem. The next set of examples is going to refer to what's known as exponential growth, which is when you're increasing in numbers, or exponential decay when the quantities are going down. So this is going to involve this general formula that you see here, along with what those different pieces stand for. Q is the quantity, Q sub 0, we call that Q naught. That's the initial quantity when T is equal to 0. So Q sub 0 is just the value that you want to use for your initial quantity. K is your either growth factor or your decay factor. Depends on if you are growing in values or decreasing in values. And T is time. If K is a positive number, I am over here right now. If K is a positive number, this is going to be a growth model because your quantity is growing over time. It's increasing in value, in quantity. If K is less than 0, so that means it's negative, that means that your quantity is going down as time goes on. Your population is going down, whatever it is you're working with. In question number 4, we have the number of bacteria in a culture. It's doubling every 3.5 hours. Assume you start with 2,000 bacteria. Somehow you know this. You have 2,000 bacteria, and so in 3.5 hours, you have twice that. That's 4,000 bacteria. For part A, we're going to find the growth rate constant, which is K, and we're going to figure out the equation that models this bacteria's exponential growth after T hours. T is your variable. And we're going to sketch the graph. A lot going on here. So your initial general formula was given above. I'll rewrite it here for you. Q naught is your initial quantity when time is 0. And your let's see. Sorry, I had to think for a second. After 3.5 hours, there, I'm back on track. After 3.5 hours, so after 3.5 hours have gone by, you have 4,000 bacteria, right? Because it doubled in 3.5 hours time. So we're going to solve this equation for K. Divide both sides by 2,000. So 2 equals e to the 3.5K. Solving for K, once again, it's in the exponent. We get it out of the exponent by taking the natural log of both sides. So now we have the natural log of 2 equals 3.5K. We divide both sides by 3.5. You get an approximation for K of, give me one second, looks like 0.198 rounded to 3 decimal places. Okay, so the formula that you're being asked for, Q of T, is your initial population size times E to the 0.198 times however many hours you would like to go by. Sketch the graph. Sketch the graph. Here we go. I'm going to try this Desmos app one more time for you. Okay, sketch the graph of the equation that we just found. Let's see, did I write that down? Okay, so we have 2,000 times E raised to the 0.198 times, I'm going to use X here, and now this is your graph. Okay, this is your graph. And let's see if I can do a screenshot. Yes, and I'm going to bring that over to our document. Put it right about there maybe. Insert this picture, and can I crop it down? That's a bit large. Okay, can you guys still see that? So that is our graph of our model that we just found. All right, check that out. How many bacteria will be present after 12 hours? All right, so 12 hours means you locate 12 on your graph. 12 on the graph is here. And you're going to go up to your graph. If this is on your calculator, you're going to get a pretty exact answer. You're just going to hit the trace button. And after you hit trace, you type in the value 12. And it should spit out the y-coordinate, which is, I wrote down 21,523. Q of 12 is 21,523.5. And we're counting bacteria. Okay. Part C, when will the culture reach 70,000 bacteria? So we want to figure out where the y-coordinate is 70,000. And I didn't give me enough space on that particular graph. Let's go over here to the Desmos picture. We want to figure out where the y-coordinate is 70,000. So if I zoom out, you're going to have to change your window pretty drastically. You're going to want your window to go from an x-min. I would go x-min from -10 to probably 25 or 30. So let's write that down in our description. When you graph this, I would say your window, I would go -10 to 30 on the x-axis. By, let's go negative, let me get this another look. Let's go negative, that's 20,000. Let's go negative 10,000 all the way up to about 100,000, just to give us some room to work with on your graph, okay? Okay, so that's my graph using a very similar window that I just wrote down for you. We want to figure out when the number of bacteria is 70,000. So you could trace along your graph until you see a y-coordinate that's close to 70,000. Or, well, that didn't work like I hoped. Or you could graph the line y equals 70,000. And that's going to intersect your exponential function exactly where that y-coordinate is 70,000. Can you see that point right there? All right, so you're going to calculate that on your graphing calculators by going to the second math menu, which is your trace menu. Go to trace, second trace, which is your math menu. And so you are going to go down to the intersect command. The intersect command is going to ask you which curve is your first curve, hit enter, which is the second, hit enter, and then it should either ask you for a guess or it will give you the guess to you. But in any case, you should get this intersection point to be at 17.956, comma, 70,000. So 17.9, let's just run that to 18. So we're going to call it 18 at that intersection point. T equals 18 hours later. Hours? I can't remember. Yep, hours. 18 hours later, the population of bacteria will be 70,000. Part D, at what rate is the culture changing in the 10th hour? So how fast is this changing? Changing means derivative, right? Okay. This is asking you, where's the first derivative? Or what is the first derivative at the 10th hour? And so if you go to your, find your derivative function, we still haven't done that, find the derivative function, plug in 10 for the value of t, that is going to tell you how quickly the culture is changing in that particular hour. On your graph, I'm not that great with Desmos just yet, but on the graph, what you would want to do is you would want to find the slope of the tangent line. Let's see if I can figure this out first. Whoops, hold on. Find the slope of the tangent line that hits the graph when t is equal to 10. Give me one more minute here. Sorry. So what is that? 10 comma, that's 20,000. Let's go down by 1, 2, 3, 4. So 5, 10, 15, 20. Let's call that 15,000. Let's see how quickly or how close I got. Yeah, okay, that looks pretty good. So the point that I just marked there in red on the graph is going to be where you would want to draw in your tangent line. Now, the slope of that tangent line is what I'm finding right now. Here we go. So q prime of 10. Q prime is equal to, oops, well that didn't make a whole lot of sense now, did it? Q prime of 10. Okay, so the derivative of my quantity function, which is way up here, so it's going to be 2,000 times 0.198, which is 396, times e to the 0.198 times 10, and that is equal to 2,868 bacteria per hour. Okay. Hopefully that's right. Okay, so I inserted the graph above, which is why my part E now is on the next page, but yours should still be where it was originally. At what time is the culture increasing at the rate of 5,000 bacteria per hour? This indicates setting Q prime of T equal to 5,000, and you can take a few minutes if you need to pause the video, solve for T. I worked it out just a little bit ago, and I got T equals 12.8 hours. So I showed you in the example before this one how to solve an equation like that. You divide both sides by the constant in front. So you're going to set this equation equal to 5,000, and you solve for t. The first thing you're going to do is you're going to divide both sides by 2,000. Once you get that quantity, it'll be what? 5 halves, I guess 2.5, and then you're going to take the natural log of both sides. That takes this out of the exponent, and then you divide both sides by the 0.198. See if you can follow that, and you should get the answer that you see here on the paper.